Hi everyone! This is Professor M. Does Science, and today we're going to be talking about ladder operators in angular momentum in another one of our videos on rigorous quantum mechanics. In the context of angular momentum, and as their name suggests, ladder operators allow us to change the value of the angular momentum by some discrete amount, therefore going up and down a ladder of discrete angular momentum values. The reason why ladder operators are so useful is that in quantum mechanics, angular momentum is quantized, and so it can only change in discrete steps. Now, this video is going to be a little mathematical because we're going to look into the details of ladder operators. But it will be really useful because we're going to use them all the time in other videos on angular momentum. And on top of that, similar concepts are used in other areas, such as the quantum harmonic oscillator, or even in more advanced topics such as second quantization. So, let's go! Let's start with a quick reminder of angular momentum in quantum mechanics, and for the full details you should check the corresponding video linked in the description. In quantum mechanics, an angular momentum operator J is an operator made of three separate components, J1, J2, and J3. The key requirement for these components is that they must obey these commutation relations. And you will remember from the video on angular momentum that epsilon ijk is the Levi-Civita symbol, and that we're using Einstein notation so that an expression like this implies a sum over repeated indices, in this case over the k indices. So this is a definition of a general angular momentum in quantum mechanics. This includes orbital angular momentum, which we typically denote by the letter L, and which plays the same role as the equivalent quantity in classical mechanics. However, in quantum mechanics, we also have this spin angular momentum without a classical analogue. If we want to specify that we're working with spin, then we typically use the letter S. Today we will keep the discussion general, so we'll work in terms of the general angular momentum J up here, and all results we derive will be valid for any type of angular momentum. As the different angular momentum components don't commute, they don't form a set of compatible observables, so we cannot use J1, J2, and J3 as the basic building blocks of the theory. Instead, we found in the video on angular momentum that the operator J squared does commute with each individual component. This suggests that we can build a set of commuting observables by combining J squared and one of the components Ji. The conventional choice is to use J3, although in principle we could have chosen any other component. So, moving forward, we will describe the physical observables of angular momentum through these two operators. J1 and J2 are still needed for the development of the theory, but since they are not part of the set of compatible observables, then we have some flexibility in how exactly we work with J1 and J2. It turns out that in the theory of angular momentum, it is often more convenient to work with a specific set of linear combinations of J1 and J2, rather than using J1 and J2 directly. I therefore introduce you to the ladder operators. As you probably guessed, the ladder operators are linear combinations of J1 and J2, and there are two of them. The first one is called the racing operator. We label it with J+, and it is defined as equal to J1 plus ij2. The second one is called the lowering operator. We label it with J-, and it is defined as equal to J1 minus ij2. At this stage, we're just going to accept that these operators are called racing and lowering operators, and collectively called ladder operators. But the rationale for these names will become clear later in the video. Ladder operators play a key role in the study of angular momentum in quantum mechanics, so the objective of this video is to work through some of the properties that will prove extremely useful in many other videos. The very first property of ladder operators is that they are not Hermitian. So they are not observables. In fact, J+ and J- are each other's adjoint operators. To see this, consider J plus dagger. It equals J1 plus ij2 dagger, and we can expand this bracket, and then using the fact that J1 and J2 are Hermitian, we get this. This is the definition of J minus. Of course, the opposite follows, and J minus dagger is equal to J plus. The angular momentum operators that we had been working with until now were J squared and then J3, J1, and J2. But as we discovered today, we can actually be flexible in how we incorporate J1 and J2 into the theory, and very often it will prove more convenient to work in terms of J plus and J minus, which are linear combinations of J1 and J2. The fact that J plus and J minus aren't observables is not a problem, because we're anyway restricted to J squared and J3 as the set of commuting observables. Therefore, from now on, we are going to consider either this set here, or this new set of 4 operators, which contains the same information. Given that this second set with J plus and J minus is very useful in many problems, in the rest of this video we're going to explore the properties of the ladder operators. The squared angular momentum is generally given by this expression in terms of the angular momentum components. However, given that we'll mostly use these 4 operators to study angular momentum in quantum mechanics, we should write J squared in terms of J plus and J minus, rather than in terms of J1 and J2. To accomplish this, consider J plus times J minus. Explicitly writing the definitions of J plus and J minus gives this, and carrying out the multiplication, we get these 4 terms. The first 2 carry through unchanged, and these last 2 terms can be grouped into this commutator. The commutator is equal to I bar J3, so that we get J1 squared plus J2 squared plus H bar J3. We can use the expression of J squared in terms of the angular momentum components up here to rewrite the sum of these 2 terms as J squared minus J3 squared. And we get to the final expression J squared minus J3 squared plus H bar J3. Repeating the same exercise with the product J minus times J plus, we get J squared minus J3 squared minus H bar J3. We can now add these 2 expressions, and this equals 2J squared minus 2J3 squared, and we can finally rearrange to isolate J squared, and we get that J squared is equal to 1/2 J plus J minus J plus J3 squared. Of course, you don't need to remember any of these, but we're going to use them constantly in our study of angular momentum, so you should either be ready to derive them as needed or simply keep a list for reference. Let's look at the commutation relations. J squared trivially commutes with both J plus and J minus. To see this, let's first write out J plus and J minus, so we get this. And then as J squared commutes with both J1 and J2, we get 0. Next, let's consider the commutator of J3 with J plus. In this case, things are not so easy. So let's again start by expanding J plus, and then we can separate this expression into 2 commutators. This is I H bar J2, and this is minus I H bar J1. So we get H bar multiplying I J2 plus J1. And this term is simply J plus, so we get H bar J plus. We can use an analogous derivation to show that the commutator of J3 with J minus is equal to minus H bar J minus. The final commutator we can look at is that between J plus and J minus. Writing out both ladder operators, we get this. We can now expand this into these 4 terms. And feel free to pause here for a second to double check this, but it should be clear after a moment. These 2 terms are 0 because they involve the same angular momentum component. this is I h bar j3, and this is minus I h bar j3, so that overall we get 2 h bar j3. So as a summary of the commutation relations, we have that the j squared operator commutes with all of j3, j plus, and j minus. Then the j3 operator obeys these commutation relations with the j plus and j minus operators. And finally, the j plus and j minus operators obey this commutation relation. Again, you don't need to remember any of these, but do keep them close because we'll also use them all the time. We're now ready to investigate how the ladder operators act on eigenstates of the angular momentum observables, so this is the exciting part. As we've been discussing, we're considering j squared and j3 as the two compatible observables to describe angular momentum, so we'll start by writing down their eigenvalue equations. The eigenvalue equation for j squared is this, where the eigenvalue is lambda, and for j3 is this, where the eigenvalue is mu. As j squared and j3 are compatible observables, we can always find a common set of eigenstates, and we'll take these states labelled by the eigenvalues lambda and mu to be this common set. Now, before we proceed, let's discuss these equations in a little bit more detail. As we discussed in the video on angular momentum eigenvalues, it turns out that lambda and mu can only take very special values. In particular, lambda is always given by j times j plus 1 times h bar squared, where j is equal to 1 of 0, 1 half, 1, 3 halves, and so on, in steps of 1 half. Mu, on the other hand, is always given by the expression m times h bar, and for a given j, m can only take the values minus j plus 1, and so on, in steps of 1, up to a maximum value of j. Despite this, the properties we want to derive today don't depend on these special values that lambda and mu take, so we're going to keep the discussion general and use lambda and mu directly. For completeness, at the end of the video, we will quote all the results we obtain using the special values that lambda and mu can actually take. Let's start by constructing a new state, j plus minus, acting on the eigenstate lambda mu. The first result we consider is that if lambda mu is an eigenstate of j squared with eigenvalue lambda, then this new state is also an eigenstate of j squared with the same eigenvalue. To see this, let's act with j squared on this state. And as j squared commutes with both j plus and j minus, we can exchange the order here and we get this. Now we can use the eigenvalue equation for j squared to get lambda lambda mu, and this leads to lambda times j plus minus lambda mu. So we see that by acting with j squared on this state, we get lambda times the same state. And this confirms that j plus minus lambda mu is also an eigenstate of j squared with eigenvalue lambda. Let's now make some room and consider j3. The result for j3 is that if lambda mu is an eigenstate of j3 with eigenvalue mu, then these new states are also eigenstates of j3, but this time with different eigenvalues that we are about to calculate. To do this, let's start with j3 acting on the state generated from j plus. And looking at the commutator up here, we can copy it. And we can rearrange it to j3, j plus is equal to j plus j3 plus h bar j plus. Using this expression, we get this. And here we can use the eigenvalue equation for j3 to get mu lambda mu, so that overall we get mu plus h bar multiplying j plus lambda mu. So what does this mean? We see that by acting with j3 on this state, we get a scalar mu plus h bar times the same state. This confirms that j plus lambda mu is also an eigenstate of j3, and the eigenvalue is now mu plus h bar. Repeating the same exercise with j minus, we would find that j3 acting on j minus lambda mu equals mu minus h bar multiplying j minus lambda mu. So in conclusion, j minus lambda mu is also an eigenstate of j3, and this time the eigenvalue is mu minus h bar. So these up here are the two equations we have just derived. If we start with j plus, the first equation tells us that j plus lambda mu is an eigenstate of j squared with eigenvalue lambda. The second equation tells us that it is also an eigenstate of j3 with eigenvalue mu plus h bar. This means that we can rewrite this state as lambda mu plus h bar. And in general, we will have some normalization constant in front, which we're going to call n plus. So what does j plus do when acting on an eigenstate of j squared and j3? It simply gives us another eigenstate of these two operators, but the j3 eigenvalue has been raised by a constant h bar. And this is the reason why we call j plus a raising operator. We can do the same by looking at j minus acting on lambda mu, which is an eigenstate of j squared with eigenvalue lambda, and an eigenstate of j3 with eigenvalue mu minus h bar. This means that we can write the action of j minus on an eigenstate of angular momentum like this, and as the eigenvalue of j3 is lowered by a constant h bar, we call j minus a lowering operator. Acting with the raising operator multiple times allows us to go up a ladder of eigenvalues every time adding an extra h bar, while acting with the lowering operator, we go down a ladder, removing one h bar each step. Hence the collective name ladder operators. Let's look in more detail at the new states generated by applying the ladder operators. If we start with the raising operator, then let's consider the norm of j plus lambda mu. By definition, this is equal to this. And the adjoint of j plus is simply j minus, so we can rewrite it like this. And using this expression above, we can rewrite j minus j plus in terms of j squared and j3, and we get these three terms. And feel free to pause here for a second to double check this, but it should be clear after a moment. Using the eigenvalue equations, we get lambda lambda mu, mu squared lambda mu, and mu lambda mu, so that we get these new three terms. The eigenstates form an orthonormal set, so we end up with lambda minus mu squared minus mu h bar. At the same time, we can write j plus lambda mu as equal to n plus lambda mu plus h bar. And its norm is then simply equal to absolute value of n plus squared. This expression and this expression are equal because they're both the norm of j plus lambda mu. This means that j plus acting on this state gives this square root multiplying the state in which the eigenvalue mu has increased by h bar. We can of course repeat the same exercise with j minus, and this is the corresponding result. Again, no need to remember any of this, but it will come in handy in our study of angular momentum in quantum mechanics. The very last thing I want to do before we conclude is to rewrite this final result in terms of the allowed values of lambda and mu for angular momentum eigenvalues, so that you can use this final answer for reference. Let's write down the eigenvalue equations for j squared and j3. And as we discussed earlier in the videos on eigenvalues of the angular momentum operators, we learned that the eigenvalue lambda is always given by j times j plus 1 h bar squared, where j can only be 0, 1/2, 1, 3/2, and so on, in steps of 1/2. And so once we have determined j, then the values of mu are also fixed and can be written as m hbar, where m can only take one of the values minus j plus 1 all the way to j in steps of 1. Knowing that the eigenvalues always have this form, then we could update the eigenstates from lambda mu to these new labels. However, to simplify notation, this is typically simply written as jm. In terms of these, the action of the raising operator on an eigenstate jm is simply equal to this normalization times a new eigenstate jm plus 1. Writing down the corresponding expression for the lowering operator, we get this. Hooray! We're done! Here, I simply have a list of the main results that we have obtained today. We'll use them in many of the other videos on angular momentum in quantum mechanics, so an easy way to keep them handy might be for you to copy them down or simply to take a screenshot. Ladder operators are extremely useful when working with angular momentum in quantum mechanics. So although this video might have appeared a little too dry the first time you watch it, we're going to use these results all the time, so it was time well invested. Check out the What Next section in the description to see ladder operators in action. More generally, ladder operators play a really important role in other parts of quantum mechanics, most popularly in the quantum harmonic oscillator. And if you want to explore more advanced topics that build on similar ideas, I encourage you to watch the playlist on second quantization. And as always, if you liked the video, please subscribe.